Good evening. Here in Japan is almost evening. Thank you for joining this my presentation. Our research topic is a numerical simulation of countermeasure against protrusion of vertical PC bars from asphalt pavement at high temperature using applied element method. I am Addisu, corresponding author and presenter from Yokohama National University, Japan. And co-authors are Professor Hosoda, Professor Hamad, and Mr. Fukaya. This presentation includes background of the study, applied element method, experimental program, and numerical modeling, asphalt pavement bending at different temperature, and simulation with asphalt pavement countermeasure at 20 and 40 degrees centigrade, and finally conclusion. This slide is about background of the study. Metropolitan Expressway is a toll road company in Japan with in Tokyo Great Area with a very high traffic volume. More than 1 million vehicles per day, and there is progressive aging. About 60% of the 327 kilometers roadways are more than 30 years old. And there is a large number of bridges, 75% out of the total kilometer. The recent investigation showed that there are around 20,000 vertical PC bars in the bridges. As you may know, vertical PC bar is installed in pre-stressed concrete bridges to enhance the shear performance. And this chart shows the number of vertical PC bars with their respective lengths. And about 93% of the vertical PC bars have less than 3 meters in length. When there is inadequate grout filling in the duct, the bar might be corroded and ruptured. And this rupture didn't show any advance warning, so it is sudden. It may damage the anchoring part, and safety will be a problem in this case. So in the past, several countermeasures were utilized by using steel plates, stainless steel mesh, and a FRP sheet. But this technique, it takes a longer construction time, which is not recommended for Metropolitan Expressway as the traffic volume is quite large. In 2018, actual rupture of vertical PC bar were investigated by the authors in the Metropolitan Expressway. And this figure shows how the PC bar ruptured by the corrosion. So if we don't use proper countermeasure, safety will be a problem. So in this study, we numerically investigate the effect of asphalt pavement system at 40 degrees centigrade on preventing the protrusion of PC bar and concrete spalling. In this study, we use applied element method to carry out a numerical simulation. And it's based on dividing structural members into virtual elements connected through springs. And this spring represents material properties and continuity between elements. And the applied element method AEM can track structural collapse behavior, starting from linear crack initiation, propagation, element separation, and a complete collapse of the structure. These are material properties which are adopted in the applied element method. This is a concrete under compression and tension and shear. And this is a bilinear material modeling. In the past, several research papers have been published on successful use of applied element method to simulate structural collapse behavior. This one is a rupture and protrusion of a PC bar. This is also part of our research. This one is a simulation, and this is an experiment. So you can clearly see that how the rupture of PC bar is energetic is. This one is a drop weight impact with polyurea simulation and experiment. This is also a part of our study, but not included in the symposium. So this is the experiment program and numerical modeling. The specimen is here. It consists of two RC members, this part and this part. They are reinforced concrete and connected together by a main bar at the center and two additional PC bars to connect them. And inside the sheets, there is no grout. Cover concrete is 0 to simulate the worst scenario in practical case. Bar diameter is 32 millimeter and tension force is 591 kilonewton applied here. And the bar is cut here 4.5 meter from the PC bar head. And in this case, the strain energy of the PC bar is around 4,400 Joule. So asphalt pavement countermeasure is provided here to consume all this impact energy from the PC bar. This is the experimental procedure, placing asphalt pavement, compacting, lifting up, transport, and setting the experiment like this. So we made numerical modeling as per the experiment. In this research, two asphalt pavement layers were utilized as a countermeasure. One is a base layer with 5 centimeter thickness and a cover layer with 3 centimeter in thickness. So to understand the behavior of asphalt pavement at different temperature and to set appropriate material behavior in the numerical simulation and to set other parameters in the numerical modeling, we carried out asphalt pavement bending at 0, 20, and 40 degrees centigrade. And this is the aim modeling of the asphalt pavement. It is 3-point bending. This is how the bending carried out, simulation and experiment. This one is cover layer at 20 degrees centigrade. Crack is originated at midspan in the bottom surface, then propagate upward until full collapse. So as I mentioned, we provide two asphalt pavement layers, base layer and cover layer. So we carried out asphalt pavement bending for both asphalt layers. This is in the numerical simulation. We utilized the asphalt pavement. The quantity model of the asphalt pavement is a bilinear modeling until the ultimate strength, then we show softening behavior in the numerical simulation as a material property of asphalt pavement. For example, this one is the cover layer asphalt pavement. This is tensile stress, tensile strain. The blue one is at 0 and the red one is at 20 and the last one is at 40 degrees centigrade. This one is the base layer asphalt pavement, tensile stress, tensile strain. And you can see at 0, at 20 and at 40 degrees centigrade. So this is a load displacement curve, which is obtained from this bending experiment and simulation. This is the load in Newton, and this is the displacement. The first one is at 0 degrees centigrade for the cover layer. And the red one is at 20 degrees centigrade, and the last one is at 40 degrees centigrade. From this load displacement curve, you can clearly see that the asphalt pavement strength is significantly decreasing, but the ductility is improved. On the other hand, the base layer asphalt pavement, the load displacement curve at 0 and at 20 degrees centigrade, it shows almost similar behavior. It increases linearly, then it shows brittle failure without any deformation. But when the temperature is increasing, its strength is decreasing, but it shows ductile failure. Another temperature-dependent material is Tacot, which is an interface bond material between the concrete slab and the base layer and between the two asphalt pavement layers. And a pool of adhesion test was carried out at different temperature, and you can clearly see its bond strength, which is highly temperature dependent. Also, this one is a numerical simulation and experiment with asphalt pavement countermeasure at 20 degrees centigrade. So the asphalt pavement, this experiment is conducted at 20 degrees centigrade, and this one is a simulation. So you can hear the sound when the bar is ruptured and impacting the asphalt pavement, but no major damage on the asphalt pavement. So asphalt pavement countermeasure was effective in consuming all this impact energy from the PC bar. So similar results were also obtained using a numerical simulation. This is how the pavement is deformed, actually 10 times magnified. This is the failure mode near the anchor, and this is illustration of failure mode in the experiment. The stress originated from the head of the nut in the diagonal shape creates a cone-shaped crack in the mortar. When the bar is pushing forward, the interface bond delamination were observed like this one. In the numerical simulation, the area inside the yellow marker where the bond lost. This is the experiment. So you can see the pavement, there is bond delamination. It means the pavement deformed over this wide area. It means it can consume more energy. And we also observe a minor crack around this center of the PC bar, like this one. You can see very few crack. This is PC bar displacement versus time. When the bar is impacting, it moves forward, but at this location, at this time, the PC bar lost almost all of its strain energy and is impacting the asphalt pavement and moved backward. We also check the asphalt pavement deformation along the center line between the two connecting PC bars. So you can clearly see that the deformation is maximum near the center of the specimen, and it's decreasing toward the edge of the specimen. So this one is AM simulation with asphalt pavement at 40 degrees centigrade. At 20 degrees centigrade, it works, but what about at 40? Because the asphalt pavement performance is decreasing with increasing temperature. Another thing is when the PC bar is impacting the asphalt pavement, the pavement might be fractured under a high loading rate. So it was necessary to consider the effect of a strain rate in the numerical simulation. So several past research also showed that the asphalt pavement, concrete are highly rate dependent. This researcher showed the strain rate with the respective dynamic increase factor. So in the numerical simulation at 40 degrees centigrade for the cover layer, this is the material behavior at quasi-static loading, which is obtained from the bending experiment, which I already explained. But when the bar is impacting the asphalt pavement, its behavior is something like this. It is highly enhanced. For this one is for the base layer. The orange one is at quasi-static loading, and the blue one is at high loading rate. So this one is the AM simulation when the bar is ruptured at 4.5 meter. It means the impact energy is around 4,400 Joule. This one is 3D view, and this one is section view near the anchor. And this one is the illustration of failure mode near the anchor. This time, two diagonal stress originated from the head of the nut and from the head of the PC bar creates a conical crack in the mortar and in the asphalt pavement. And as you can see, the asphalt pavement is severely damaged near the anchor. And we also observed that there is a big crack around the corner like this. And we also observed that there was severe bone delamination between the concrete slab and the base layer. So when the bar is impacting the asphalt pavement, since it is the position is vertical, the entire pavement system will fall down. This is a PC bar displacement versus time. In fact, the bar is impacting the asphalt pavement, and finally, when displacement reaches 130 millimeter, it stops moving. Anyway, at this temperature, when the bar impact energy is 4,400 Joule, the pavement system were not effective according to this numerical simulation. So we extend the numerical simulation by reducing the impacting energy. We just change the rupture distance at 3 meters so that the PC bar impacting energy become around 3,000 Joule. So this time only thin layer of covering asphalt pavement were spalled off, but no, the PC bar was almost kept inside. In fact, there is some crack near the corner, but the pavement was still on the specimen. I mean, there was no fall down compared to the previous simulation. This is the interface bone delamination between the concrete slab and the base layer. So we also carried out similar simulation by rupturing the PC bar at 2 meters. This time the impact energy is around 2,000 Joule. This time almost no severe damage, just thin layer of cover layer asphalt pavement were spalled down. This one is the PC bar displacement versus time. When the bar rupture length is 2 meters, the impact energy is too small, the protrusion is also small. Whenever you increase the rupture distance, it means you are increasing the strain energy and more impact and more damage and more protrusion. Similar simulation is carried out without using countermeasure. This one is just for reference to show how the asphalt pavement were effective in consuming or dissipating the impact energy from the PC bar. This one, as you can see, the bar is erupted and displaced around 3 meters. So you can imagine how much amount of the energy is consumed by the asphalt pavement. So based on the result obtained in the present work, the following main summary, remark, and conclusion can be drawn. Appropriate numerical modeling simulation with applied element method can be conducted with appropriate modeling of asphalt pavement layer, properties of the interface material between concrete slab and asphalt pavement, and by considering the strength rate effect in the asphalt pavement. Second, performance of the base layer asphalt pavement and cover layer asphalt pavement were reduced with the increase of temperature. On the other hand, with the increase of temperature, the failure mode of the asphalt pavement was shifted to ductile failure. And according to the numerical simulation, the asphalt pavement system at temperature of 40 degrees centigrade could not prevent 4,400 joule impact energy. On the other hand, similar simulation with the 3,000, around 3,000 joule impact energy were effective. Finally, the strain energy of the PC bar was dissipated by a simultaneous action of asphalt pavement deformation, asphalt pavement crack, and crack in the mortar, and interface bond delamination between the concrete slab and asphalt pavement. So in the future, we will improve the asphalt pavement materials which can survive this much amount, 4,400 joule impact energy. And the asphalt pavement countermeasure at low temperature will be also carried out. And countermeasure under the bridge girder will also be carried out. This time only we focused on the upper part of the bridge girder. So this is all about my presentation, and thank you for your attention.
Okay, Addisu, thank you very much for your presentation, for your interesting and interactive slides. For now, I think we have no question in the chat and in Q&A section, but I have made some notes under your presentation. It's really interesting. What software did you use for numerical modeling for your experimental? And if you can you tell in more detail about the, I don't know, boundary conditions, the law of deformation of materials that you used to get such results, which I think were very high level of accuracy with experimental data, I think.
Yes, actually, we use the applied element method, which is not finite element modeling. And this modeling is more suitable to simulate progressive collapse of the structure. Actually, sorry, these are a material behaviors which are adopted in the numerical simulation. For example, in this case, this is also a part of our research. So what I did in the numerical simulation for the boundary condition, for example, basically this is the full scale, this is the experiment, but in the numerical simulation to reduce number of elements and unnecessary part, we omit this part, the red part, which is not necessary in the numerical simulation. This part is the most important part in our research. So we avoid this, the second part of the reinforced concrete member, and we restrain the sheath or the duct, fixed support, so it cannot move. This part of the reinforced concrete, we make fixed support at the connecting PC bar, so it cannot move anywhere. So we apply the asphalt pavement, then the bar, although during tension force, it moves only in this direction. Then after cutting the bar by removing one element at second state, then the bar will move forward. It is free, so it can impact the asphalt pavement.
Oh, and about software, is it commercial software or it's software from your university?
Actually, this one is in the university we used for research purpose, but you can also find commercial software.
Okay.
It is already outsourced.
Okay. It is interesting for experiments. I see that we have some limitation to use this method and this program. It is faced with boundary conditions, the right data for boundary condition. It is one of the main things, I think so, to make the right calculation. And did you have some comparison table with experimental data to be proved that your modeling is good? Some comparison.
Yes. Actually, from the beginning, this one, although a part of our research, you can see the simulation and the experiment. So it was from the beginning, the numerical simulation were validated with the experiment.
Okay.
This one is although similar, it is a part of our research. This one is although at 20 degrees centigrade. The simulation is already validated with the experiment, and we found a very nice result with the experiment. What we did is just we extend to at 40 degrees centigrade. In fact, it will be validated with the experiment. Actually, it is already validated with the experiment, but unfortunately, the simulation were carried out in last October, I think. But last month, experiment and simulation was carried out at high temperature, even at 50 degrees centigrade, and it was very effective in absorbing the energy, and it works quite well, but not included in this symposium, unfortunately. In every step, we validate the numerical modeling with the experiment. But this particular case, it should be validated with the experiment because this is a safety management and it should be working very well in every circumstance.
Okay, thank you. We have some questions from Jean-Michel. Is this common? Is this use of PC bar specific to Japan? Because in Europe, I have not heard of such rupture. And do I understand that you expect the pavement to avoid the protrusion of the bar?
Maybe Dr. Kasuga knows very well about this one, the use of vertical bar in the bridge. Actually, there are around 20,000 vertical PC bar in the Metropolitan Expressway. It is in the Tokyo Great Area. Our project scope is also for this particular area, actually. And we also observed such kind of rupture by the authors in 2018. So the problem is such kind of rupture didn't show any in advance warning. And it is a toll road. There are so many vehicles running over the pavement. And even this, if this incident is happening, maybe maintenance time, closing the road will be a big problem. I think it is better to mitigate this problem in advance rather than waiting until the problem is occur. And the other problem is out of these 20,000 vertical PCUR, which one had the problem, grouting problem, which one had the corrosion problem? No one knows. They are embedded inside the concrete.
Okay, I understand. Maybe some questions, maybe someone from my colleague.
Brad, I have some comments and questions. Okay.
Please.
Yeah, thank you, Adis. So I add some comments against the Jean-Michel questions. So the Metropolitan Expressway, relatively very old, but more than half centuries, and they are built before the last Tokyo Olympic game. So the bar is come from Dividak, and also the Jean-Michel, the country of the Freycinet, they don't use this kind of bar. And at that time, the grouting is very poor. So we have a problem, this kind of. So this is very important research for the Japanese infrastructure. But nowadays we don't use any vertical bars. So, and I have a question. And please tell me why do you choose 40 degrees? Because during summertime in Japan, especially pavement temperature in the more than 40, I imagine. So the 50 or sometimes 55 degrees. So do you extend your research to the upper 40 degrees?
Yes, thank you for your question. As you said, even this time it is summer and the pavement temperature, we clearly understand the pavement temperature can reach 50, 60 degrees centigrade, not at 40. This one is just for the beginning, actually. We just checked at 40 degrees centigrade. Because before carried out the experiment, simulation is all carried out in advance, always. So we checked at 40 degrees centigrade. But later on, we confirmed that 40 is not enough. So as I mentioned earlier, last month's experiments were already conducted at 50 degrees centigrade, not 40. So it was effective against that temperature. And another thing is we have although a plan to extend this one at low temperature. Yes, I understand that in Tokyo area, the temperature not that much below 0, not like Hokkaido area, north part of Japan. But it should be checked at low temperature, maybe -10 or at 0 at least. Because the pavement, asphalt pavement behavior is changing with respect to temperature.
Okay, so I'm interested in your further research. Thank you, Adis.
Thank you.
Okay, we have some additional comment from Jean-Michel about his question. But you mitigate the protrusion, not the rupture. How you can comment?
Sorry, again?
You mitigate the protrusion of the PC bars, not the rupture.
Yes. Actually, regarding the rupture, I'm not considering that. I just focus on the impacting the protrusion and the impacting something like that. Not the problem is already there. It is mostly poor grouting problem. So this problem is still exists. I mean, as Kasuga, Dr. Kasuga said, these are constructed several years ago. In fact, this problem is already solved this time. No such kind of problem, but the reconstructed 50, 60 years ago, they are still under service. So I don't focus on such kind of rupture of the bar, but I'm focusing after the rupture of the bar, protrusion and impacting, something like that.
I think this comment appeared from your topic. You said against protrusion of vertical PC bar using applied element methods.
Vertical, actually, in our case, it should be vertical, but the experiment and the simulation is almost like in horizontal position. We made it just for suitability of the experiment because the bar length this time is 5 meters, and we cannot rotate into vertical direction. It is very difficult. So
okay, I understand. I'm talking about protrusion and rupture, the terminology about this different things. Okay, I think we have finished our session. Yes.